Okay, so let's go over a little bit of the theory and some of the calculations that you will need to do for experiment 3 on calorimetry. Okay, so the first part of the experiment, you were asked to calibrate the calorimeter. Okay, so let's take a quick look at your setup. So you had two styrofoam coffee cups. You had a lid. On top of that, you had a temperature probe to measure any temperature changes that took place. Okay, so the system up here, that is the coffee cups, the lid, the temperature probe, and the liquids. The liquids, of course, being your 1 molar sodium hydroxide and your 1 molar hydrochloric acid. Okay, and the surroundings that I've shown down here, that's everything outside of the system. And in this experiment, you're assuming that no energy is being transferred to the surroundings. And you might want to think about that assumption, whether that assumption is valid or not. But if we assume that, okay, the first law of thermodynamics can be stated like this, that the change in energy of the system plus the change in energy of the surroundings is going to be equal to 0. And so if we assume that no energy is transferred to the surroundings, therefore the change in energy of the system is going to be equal to 0. Okay, and so we look down here at this equation. We have that delta E of the system is going to be equal to the heat that's transferred to the cup plus the heat that's transferred to the solution plus the heat of neutralization. The heat of neutralization, that's going to be an exothermic reaction, so that'll be a negative number. So when we sum these three terms together, we should get 0 kilojoules. Okay, so let's look at each of these terms in turn. So the heat that's absorbed by the cup, that's going to be equal to the heat capacity of the cup, so that's the C cup over here, times the change in temperature of the cup. Okay, so the change in temperature of the cup, that is the temperature that you recorded after neutralization and the system has reached equilibrium. The next term is the heat that's absorbed by the solution. So the heat absorbed by the solution, that's going to be equal to the heat capacity of the solution, and the heat capacity of the solution that's given to you in your lab manual. And that's multiplied by the mass of the solution, okay, and that's the data that you recorded in your data sheets, again multiplied by the temperature change that you observed in the cup. So the final term, which is the neutralization term of over here, that's going to be equal to the change in enthalpy of neutralization times the number of moles of limiting reactant divided by 1 mole. Okay, and so if we look down over here, we see that if we have 1 mole of HCl and we mix that with 1 mole of sodium hydroxide, the amount of heat that's going to be released is 57.3 kilojoules. And that's the heat released if you were to combine 1 mole of HCl and 1 mole of sodium hydroxide. Of course, you guys didn't add 1 mole of each of those. Down over here, you added approximately 50 milliliters. Okay, well, what you recorded actually was the mass of both of those solutions. And if you assume the density of those solutions are 1 gram per milliliter, you can then determine what the volume is that you added. Okay, and so the one that comes out to be the smallest volume, that's going to be your limiting reagent. And then you can use that to calculate the moles of each of them using molarity times the volume. And once you've done that, you would have every term in this equation over here, and the only one that would be unknown would be C cup. So you can rearrange the equation and solve for C cup, and that will be your heat capacity term for that cup. And you use that for your subsequent experiments. Okay, so part 2 of the experiment, you were asked to verify Hess's law. Okay, so let's look over here. So what we do know is up here we have delta H1 is equal to delta H2 plus delta H3. So we have 3 reactions here. So reaction 1 is calcium metal with some acid added, gives you calcium, aqueous ions plus hydrogen gas plus 2 waters. Okay. Reaction 2 is, in this case, you added water and you get calcium hydroxide and hydrogen. That gives you delta H2. Reaction 3 is, now if you have that calcium hydroxide and you add acid, you again produce calcium ions plus water, and that's delta H3. And so if you add reaction 2 and reaction 3 together, that will give you reaction 1, right? So let's think back to what you did experimentally. So what you did experimentally is you added calcium to an acidic solution followed by the addition of water. And then you did the reverse. You added water followed by acid. So do you expect reaction 2 followed by reaction 3 to give you a different result if reaction 3 was followed by reaction 2? Maybe you want to think about that, okay, if that's the case or not. So the final part of the experiment was part 3, and here you took an unknown salt and you dissolved it in water. Okay, so the total energy, or the change in energy of dissolution, that's going to be equal to the change in energy of the lattice plus the change in energy of cation hydration and the change in energy of anion hydration. Okay, and in your experiment, you would have either observed a decrease in temperature or an increase in temperature. So an increase in temperature would indicate that it's an exothermic reaction, whereas a decrease in temperature would indicate an endothermic dissolution process. So the energy of the lattice, that's the energy required to break a mole of ions into separate, positive cations and negative anions. Okay? And that's always an endothermic process. And so the example I'm using down here is sodium chloride. Okay? And so its lattice energy, it requires 778 kilojoules per mole to break a mole of sodium chloride into its cations and anions. Okay? So delta E of cation hydration, this is going to be an exothermic process, because we can imagine the positive cations interacting with the water molecules having an attraction to each other, and that's going to release energy. So that's minus 390 kilojoules per mole. And then we have anion hydration over here. That's also going to be an exothermic reaction, and that's going to release minus 377 kilojoules per mole. So when you add these all together, the net result is 3 kilojoules per mole. So if you were to dissolve sodium chloride in water, you would expect it to be an endothermic process.